Okay, we'll go ahead and start. So good afternoon to everyone. Welcome back to DFI's Impact webinar. DFI's Driven Pile Committee hosts this webinar 3 to 4 times per year in order to present on pile-related developments, current practices, and case studies. If you have a topic that you would like to see, or even better, if you have a topic you'd like to present on, then please reach out. My name is Travis Coleman. I work for GRL Engineers. Just some housekeeping stuff. We'll all be automatically muted during the presentations. And if you have a question, we will address those for all 3 presenters at the end. So please use the question and answer function within the website. I'll monitor those questions and then we'll dish those out at the end of the presentations. So today we have 3 presenters, and the overall theme is non-traditional piles and pile installation methods. Corey Sechler from Creative Composites will be presenting on fiberglass reinforced polymer piles. Brendan FitzPatrick from DuroTerra will talk about ductile iron pipes. And Ian Vaz from GIKEN will discuss press-in piling installation methods. And that's it. We will get going right away. So Corey, you will have control.
Wonderful. Well, thank you for joining me, everyone. As Travis introduced me, my name is Corey Sechler. I am the Technical Sales Manager for the Creative Composites Group. And today we want to spend just a few moments with you talking about fiberglass products. And so generally when you use the word fiberglass, a lot of people they think of that pink itchy stuff that's in your house. And, we don't really think about fiberglass in the sense of a product that could be a sheet pile, a structural pile, a fender pile, a large camel for the Navy. That's a submarine camel that you see in front of you, or maybe a floating log style camel that the Coast Guard would utilize in the lower right-hand corner. So what I wanted to do today is just spend a few minutes talking about fiberglass reinforced polymer. And we're going to touch on our hollow pipe piles and really stay focused on that for the majority of our conversation. So we manufacture round fiberglass pipe piles in diameters ranging from 8 inches to 78 inches in diameter. Now, to date, a majority of our round fiberglass pipe piles have been used in bridge fendering applications, kind of like this example that you would see in front of you from New Jersey. Those are 24 and 36-inch diameter piles behind that fender system that hold all of that in place and protect that bridge pier from vessel collisions and elisions. So why is fiberglass utilized in marine environments? Well, recently we've seen a trend where steel, wood, concrete, traditional materials are rusting, rotting, and corroding at a more rapid pace. Fiberglass products have been designed with a longer service life, or intention of a longer service life. So we're seeing folks like out in California at the West Harbor Marina. Those are fiberglass piles as a mooring and fendering pile in their system. We see folks like Compass Minerals in Franklin, Louisiana, replacing some of their traditional components with, again, a fiberglass piling product. At this facility in Franklin, Louisiana, they happen to load around 14 barges per day of salt. So it's a very caustic environment, right? A lot of salt getting on all of the equipment and everything like that. They've replaced the traditional components with a fiberglass pile. And so we'll see folks even like the U.S. Navy, who happens to be our largest customer and user of fiberglass hollow pipe piles. They use these in a dock or pier fendering application where we're trying to protect that pier and the vessel from that collision or abrasion onto the pier itself. We've worked with folks like the Port Authority of New York and New Jersey, New York City, and San Francisco ports, just to name a few, with, again, replacing traditional components, maybe it's concrete, steel, or timber, with a fiberglass piling application. This happens to be berth 18 and 19, or berth 4, or berth 6 at the Port Authority of New York and New Jersey. You'll see some of our 12-inch diameter fiberglass piles. In this application, because they wanted additional crush resistance, they happened to have filled these piles with concrete. 2012 was a unique year. Hurricane Sandy came up the East Coast, and during that event, the Statue of Liberty's pier was destroyed. This became a Federal Highway Administration project, and they chose fiberglass piles. Those are 16-inch diameter piles driven to bedrock and then cut to grade with a Greenheart timber decking on top of it. And in their mind, it was kind of the best of both worlds, a fiberglass product in the oxygen zone, so it's not going to corrode or rust or rot away, and then a Greenheart timber decking on top of it to give it that, I'll call it curb appeal, that the Federal Highway was looking for the Statue of Liberty pier. Now, I've mentioned fiberglass in use over traditional materials because of our resistance to rust, rot, or corrode. But fiberglass has some other advantages. Our modulus of elasticity is generally around 1/6 to 1/10 that of steel. So we're normally in the 3.5 to 5.5 million range. And so we have, again, manufactured piles in diameters ranging from 8 inches to 78 inches. And with that lower modulus of elasticity, we're often able to be utilized in unique ways, such as the JTA ferry system in Jacksonville, Florida. So this is a fiberglass pile system that's capturing this ferry as it comes in. Because of the river current, wind load, and even sometimes vessel speed, this vessel used to impact a rigid structure, and sometimes it would knock over pedestrians or even motorcycles. So the decision was made to replace the traditional system with a fiberglass system that's going to bend and deflect and capture that energy during that vessel collision or elision. We've worked with folks like Texas DOT to replace traditional dolphin pile clusters with fiberglass piles. And most recently, we've worked with the Jamestown ferry system. Actually, this is probably going back as far as 2014. But the Jamestown ferry system has been working to replace some of their traditional dolphin clusters, their wooden dolphin clusters, with 48-inch diameter FRP piles. These piles are around 75 feet in length, 48 inches in diameter. And during this collision, they will bend, deflect, and move at the top somewhere around 3 to 5 feet, depending upon the impacting energy. But again, why fiberglass? In some of these cases, it gives you more of a impact absorption. Wait for the video to close. We've recently been working with folks like Maine DOT in more of an axial and bearing capacity application. So Maine DOT has chosen to utilize FRP shells, I'll call them that, to encase some of their concrete, their H-pile, their rebar cages on various bridges. So this year we'll have worked on 4 separate projects, Mariaville, Southport, and 2 others, with an FRP casing and piling system, both in a protection, I'll call it a stay-in-place form, and also as a axial or bearing pile itself. We've done work with folks like the Coast Guard in replacing ATON piles, so aid to navigation piles. Now, the Coast Guard's taken a little bit of a different approach to this. They've looked at fiberglass as a non-traditional material, and they've said, listen, if we could put fiberglass in, it may cost more than a wood pile or a concrete pile, but if it lasts 2 times longer, maybe even 3 times longer, the service life cost of this product is far less than replacing a traditional component on a more cyclical nature. We've done work again for the U.S. Navy. As I mentioned, they're my largest customer. This is Point Mugu in California. Great example here. They were having problems with some traditional materials during heavy storm surges. So Point Mugu, this is the U.S. Navy runway light pier. Really, it's necessary for when those Navy planes are landing. But you'll see the unique thing here is that's all fiberglass components, fiberglass pile, structural members, railings, handrail, all that fun stuff, fiberglass. Most recently, we've had a contractor out on the West Coast, Cushman, work with Moffett and Nickel on the Capitola Pier. So about 1.5 years ago, the Capitola Pier sustained heavy damage during some winter storms. And so Moffett and Nickel, the engineer of record, chose to utilize around 160 16-inch diameter fiberglass piles for this project. Those piles range in length from around 30 feet to 65 feet in length, to form up that bent system of the new pier. We've done a lot of work with things as small as, well, just little boat lift piles. We've done floating dock applications, be it in Florida, New Jersey, Maryland, or even California. And we've recently been introducing some of our fiberglass piles, again, in an axial or bearing load capacity for things like travel lifts. So this is a small marina application right above Norfolk, Virginia. And there you can see some fiberglass piles. Those are 16 inches in diameter with a precast concrete cap on top of it to form the bottom of that travel lift system. So folks often ask me, how do you put this crap in? What's it take? The answer is your traditional equipment. Our fiberglass piles have been installed with a diesel, vibratory, or a drop hammer. And I should probably add a fourth application. We've had some recent contractors use a vibratory plate compactor as well to install our product. So generally, again, be it diesel, vibratory, or drop, we're going to grip a hold of the side of the piles. We always recommend that our contractors order the piles at least a foot longer, if not, maybe 2, to handle any damage that's going to come from the clamping, abrasion, or rips from the clamps. So we've had some contractors utilize male and a female mandrel system as well to pick the piles up and then place them. We often get asked, can you splice these products? The answer is yes. There is technology out there. We manufacture splices, inserts, and sleeves wherein we can splice piles. So the example and the photo on the right is the Ravenswood Bridge right outside of the Fort Lauderdale Airport in Florida. So because of the overhead power line restrictions, these piles, which needed to be 95 feet in length, had to be produced in around 30-foot lengths. So the contractor drove the initial stage, put that sleeve on there, added our adhesive bonding agent to it, let it cure for 24 hours, and then drove it the next stage. Again, added another sleeve, and then finally drove the third and final stage to tip elevation. Sometimes we'll add paint to our product. Is it necessary? No. It's just an extra layer of preventative maintenance. So in some applications, our piles will go out there without any paint or coating, and some owners, agencies, have asked us to provide that coating technology to give us additional UV resistance. So I've been telling you a lot about fiberglass piles, and to date, most of our piles have been used in a fendering application, an energy absorption application, if you will. But most recently, we've been working with several clients in Florida, Virginia, New Jersey, and other places with column loading. Fiberglass piles have been utilized as axial or bearing piles for restaurants, houses, and most recently, a 3-story office building that's underway in Ocean City, New Jersey. So because we're a long, slender column, we're going to follow Euler's buckling for you engineers out there. I won't bore you with all the details right now, but within our technical literature, we can list all of our ultimate column loading capacity and all the fun equations and things like that. We've done a lot of work with PDA analysis. This example that I'm going to show you is 2014 with Crofton down in the Norfolk area. So we took a 16-inch diameter pile and set up on it with 2 different hammers, a Vulcan 01, and then finally an APE D30 hammer. And after 2 days of various testing and whatnot, we finally hit a point where we didn't fail, but the plywood pile cushion actually flipped over onto its side and was driven down through the pile. But after 2 days of driving, we achieved around 235 blows per foot, or a driving resistance of around 340 kips with our pile. And if you have any questions about PDA analysis or things like that, we'll gladly share that information with you. We've got all that documentation. Skip over this slide for a second. I want to spend a few moments about talk about composites, because people have a lot of questions. What is it? A composite is actually, concrete is a composite because it's composed of various materials. Concrete has your sand, your aggregate, and your cementitious material in it, right? Along with water. So our composite piles are manufactured out of rovings, mattings, and UV veils coupled with a resin system. So Fiberglass composites are an orthotropic material, which means our properties are different along each axis. And that's something for you to consider whenever you drive them or even think about designing with them. They most closely resemble wood with how we're going to design a fiberglass pile. And again, just trying to give you the broad brush approach today rather than dive into all the details. But fiberglass is an orthotropic material. Our properties are different along each axis. Keep that in mind. We can talk about properties like our tensile strength. We can be stronger than A36 steel, although we have little to no yield. So basically, we consider failure as 30% of our ultimate load, a 30% reduction in our ultimate load. We can go on and talk about compressive strengths and how we stack up against aluminum and everything like that. And so I apologize for, again, not diving into the details, but as an engineer myself, it seems like each individual case is unique. So we'd be more than happy to answer questions at the end of this conversation with any questions, concerns that you may have. Again, I mentioned our modulus of elasticity is generally about 1/6 that of steel, which means that we can bend, deflect, and absorb more energy than steel because steel is a very rigid system in a fendering application. We manufacture our piles through two main processes. One is the pultrusion process, where we pull, hence the name pultrusion, but we pull a bunch of rovings up through a forming and curing die, introduce resin to it, hit it with heat, and we have an instantaneous thermal set product, which comes out the other end, and we can manufacture piles up to around 115 feet in length. We also manufacture some of our piles out of a vacuum infused process. So our larger diameter piles, 24, 30, 36, 48, and right now we're making some product that is 72 inches in diameter, but they would be manufactured through a vacuum infused process. Again, I mentioned our mechanical properties. We have several brochures with our mechanical and technical data in them. And right now, there is some guidance within the industry on LRFD. We've done a lot of testing. So whether you're designing by LRFD or ASD, our literature helps you with that backup data. The LRFD pre-standard, I misspoke. That's actually now an actual standard, but the LRFD standard for pultruded profiles is available. And just as if you were designing a traditional steel, wood, or concrete product, you can have the additional fee factors, reduction factors, and all of that wonderful information is in this standard at your fingertips. So again, we make piles up to 115 feet. This says 110, but somewhere in the 110 to 115 feet in length is what we can manufacture. So why composites? It's because we are corrosion resistant, so no maintenance, higher strength, similar to steel in some directions. We're lightweight, 80% lighter than concrete, and we can custom mold some of the sizes and shapes that you need, and we have some design flexibility. We call it a lot of reverse engineering. Many times engineers will approach us and say, hey, I'm currently utilizing a steel pile, a concrete pile, a timber pile. Can you reverse engineer this into an FRP product? And the answer is yes, we can. And most importantly, we are 100% domestically sourced. We have factories in Houston, Texas, and Western Pennsylvania, Dayton, Ohio, and Augusta, Maine, just to name a few. So this is us, the Creative Composites Group. I look forward to your questions at the end. Thank you.
Corey, thank you very much, and you hit it perfectly on time. So thanks for that as well. Everyone, please get those questions in the Q&A chat box as these presentations continue. And Brendan, you have control.
Wonderful, excellent. Thank you, Travis. Thank you, everybody at DFI, for organizing this event, and thank you to the audience for participating here. My name is Brendan FitzPatrick. I am the president of DuroTerra. We are a distribution company that focuses on ductile iron piles, and so we'll spend a little bit of time getting into the presentation. There we go. So Corey mentioned being an engineer. I myself am a geotechnical engineer as well. And, a big part of what brings many of us into this industry are the challenges, right? And every job has its challenges. And so when we start thinking about foundation challenges, we start looking at the geotechnical challenges. And many times, if we're dealing with a site that has soft or loose conditions, we oftentimes start thinking, okay, maybe shallow foundations or intermediate foundations aren't going to work. So we look at deep foundations, right? And then if you couple that with high loads, then certainly heading towards a deep foundation. And so those are the geotechnical and structural design challenges. But what we oftentimes find is that there are more practical challenges that also heavily influence the foundation selected for a project. So those might include things like, are you working on a building addition? Is there going to be access? Is it a constrained site? Are you working in an urban setting and you don't have a lot of laydown room or area to work? Are there vibration concerns? Are you working inside of an existing building or working adjacent to one, and you're worried about vibrations generated during the deep foundation installation process? Things like overhead clearance. Are you working in a basement application? Maybe it's a high bay warehouse, certainly not something where it's open to the air above. And so all of these types of challenges oftentimes are very practical challenges, but they many times will influence the foundation selected. And being that this is a driven pile committee webinar here, many times these practical factors will oftentimes rule out a traditional driven pile. And so this presentation is going to focus on another option there. And so when we look at what options we're talking about, many times, there's lots of different deep foundation options. And just to show a few there, many times we're talking about now a driven pile application that could be used as an alternative to most commonly things like helical piles or a micropile application. So for those of you that have not seen the ductile iron pile system, this is what the system looks like if it was to show up on your project site. So this is a modular system that is composed of a ductile iron material. So it's similar to that manufactured for water transmission, but it's actually designed specifically to take driving stresses associated with a percussion hammer. And so it's on each pile section, you have a taper as well as the opposite end that has a socket in it that allows you to benefit from the very rapid plug-in drive connection. And you can see the typical setup on the right-hand side. That's a medium duty 20 to 30 ton excavator with a hydraulic percussion hammer. So just a note about the hammer. Many people think it's vibratory. It's actually not vibratory. It is a driven pile, but it's just very high frequency in a percussion fashion. So when we look at some of the material properties of the system, the system is manufactured in a variety of different pile diameters as well as wall thicknesses. That generates structural working capacities on the low end from about 25 tons up to more than 100 tons on the high end. Typically using properties like 46 KSI for a yield stress, so similar to a grade 50 steel. And then elastic modulus that is a little bit less than steel at 24,000 KSI. A couple of the important aspects, it does have, and it's manufactured to have high impact resistance, which is important as you're driving these things in the ground. And also you see an enhanced corrosion protection compared to steel. So when you're looking at design, we also oftentimes will take that into account. So one other aspect is that it is 100% recycled material. And so particularly nowadays, when we're talking about sustainability and sustainable foundations, it does have that benefit. From a construction perspective, some of the benefits you might see. So first of all, the versatility in the installation, and we'll talk about how you install these in just a minute. Installation rates that range from 500 to more than 1,000 feet a day. So it's a very rapid installation approach. You compare that to things like micropiles that are oftentimes 2 or 3 times slower than what you see with ductile iron piles. Relative to the material, because it is modular in nature and it shows up on your site as a bundle of pipe, essentially. It's easy to have that material offloaded from a flatbed. And then in terms of handling and whatnot, it's very safe and you can stack it on site. So you don't need a lot of room to be able to install the system. We mentioned the plug-in drive connection already. That allows you to be able to make very quick field connections to virtually drive these any length without a slow, time-consuming welding process in the field. And then the last thing we'll touch on a little bit later on is it is a low vibration system, particularly because of the high frequency impact energy that is used to drive the pile on the ground. So when we look at the different types of installations, the first is just more of a traditional type of driven pile, and that would be what we refer to as a dry install. That's where you're putting on an end cap, driving that drive shoe in the pile down until you essentially terminate on something very hard. That's really generating capacity by going down to rock or very dense glacial till or very dense sand. Alternatively, you can install it with a wet installation approach, which creates an exterior grouted displacement pile. And you're doing that by driving an oversized shoe and then continuously pumping cement grout as you drive. And we'll talk about both of those options here in a second. So the installation with a dry approach, so you can see on the left-hand side, you basically cut the taper off of the first section. You put on your drive shoe, which could be a rock point or it could be a heavy-duty flat shoe, and line the pile up and start driving. You'll notice in the second picture there's the white marks. Those are 1 meter marks. And so each of the piles factory marked. And so it allows you to monitor drive rates as you advance the pile. Once you drive the first section in the ground, you would simply reach over with the excavator, grab your next section, drop the taper into the socket and continue driving. And then you would advance the pile until you essentially hit your termination layer. And so much like a traditional driven pile, whether it's pipe or H-pile, you're going to drive these things until they essentially hit a set. And so you can see what that looks like on the right-hand side, a typical drive rate, which, driving through an urban fill, maybe it's some variable drive rates, and then you get into some soft soils. In some cases, you may even just push through very soft soils, and then the drive rates start to slow down as you get into more competent material. Now, for this pile to set in order to get the full capacity, many times you're really attempting to get down to a rock or partially weathered rock or very dense glacial till, something that's got blow counts that are 50 over 1, 50 over 2 inches, 100 over 1 inch, that type of thing. So it takes a really competent material to develop that full structural capacity. Alternatively, if you're looking at doing a grouted displacement pile, you can see on the left-hand side, you've got the oversized grout shoe with the pile in the center there. You'll also notice that there's grout ports that are shown on the pile, and those see right there and there around the side. Those allow you to, as you start to drive the grout, you're going to pump a grout mixture through a grout box that goes down the center of the pile, interior of the pile, and out the grout ports. And it's basically fills the interior and then fills the annular space around the pile that's created by the oversized shoe. So as you drive, you would do it in the same fashion, but this time you're pumping grout and looking for that grout return around the exterior of the pile. And then once you get that first section in the ground, you just simply pull off, grab your next section, put it in, and continue driving while you're pumping. And the end result is what you'd see on the last slide there, or last picture there, which is a fully encapsulated grouted pile. That works really well for developing friction capacity when driving to rock maybe is impractical. So when we look at a versatility of installation, you can see a variety of different pictures here. Working from variable grades is very easy with the system. You don't have to set up specifically at the pile location with a flat working pad. Working within building interiors, typically overhead clearances, you're looking for about 18 feet or above is the primary type of application there for interior work. But you can also see very tight access, or in the pictures on the right, or working right next to adjacent structures with very low vibrations. You can see what those vibrations levels look like. Generally speaking, you're looking at peak particle velocities that are less than about 1 inch per second. Many of the sites, it's closer to about 1/4 to 1/2 inch per second. And one of the keys is that it does dissipate very rapidly with distance. By the time you're a few feet, 5, 6, 8 feet away from the pile, it's very low levels. So very different than a traditional driven pile. So to illustrate some of the examples of experience, as well as a little bit of the design, we'll go through a couple of quick project summaries here. So this was a project done in Boston area for Boston College. They were building a new basketball pavilion, and it involved a demolition of the existing part of the existing structure, and then 36,000 feet of new space at the existing Conti Forum arena. The design team was going to reuse a number of foundations, but also had some new foundations with loads up to about 600 kips. You can see the soil profile on the right-hand side. Generally speaking, it was 10 to about 20 feet of a debris fill material, sand, gravel, bricks, boulders, highly variable. You see blow counts that range from 8 to more than 75, and then underlain by a medium dense to dense sand, followed by rock. And so because of the tight proximity in this area and potential for overhead clearance restrictions, the design team specified 75-ton drilled micropiles, as well as 75-ton ductile iron piles. And so the project was put out to bid, and essentially, one slide too many, ductile iron piles were selected based on overall cost savings as well as schedule savings compared to the micropiles. The contractor, Phoenix Foundation Company, was selected to do the work, and they installed a Series 179-0 pile. So that's basically about a 6 3/4 inch material, OD, with a wall thickness that's about 0.35 inches. The piles were planned to be driven down and set on rock for capacity. So from a design perspective, on a structural approach there, it is composite in nature, similar to a micropile in the sense that you do have the pile itself that's going to act as the outer casing material, and then you do have an inner grout, and if desired, you can put a center bar in there as well. And so you have those different components. Ultimately, for that size pile material, you're going to generate a capacity that's about 93 tons as a working structural capacity. Now, if you look at from a geotechnical capacity, because these were going to be driven down to rock, it's really about driving down, developing a project-specific set. We say oftentimes less than 1 inch in 50 seconds or more as a guideline, but developing that project-specific set and then verifying through full-scale load testing. So that's what was done. The load test, actually, if I jump back real quick, you can see that top picture, actually, they're installing reaction piles. Those were with oversized shoes and essentially a grouted displacement ductile iron pile. And so those were all driven, both test pile and reaction, to about 28 feet, where they all hit set on rock. The test pile was instrumented with strain gauges as well as a telltale. And you can see the results performing the load test up to 200%, about 150 tons, and about 3/4 of an inch of movement, total movement upon rebound, just over about 1/10 of an inch. So a lot of that was elastic movement of the pile. And then in Massachusetts here, we oftentimes have to show that the load is getting down to the bearing stratum. So strain gauges helped us show that more than 170% of the design loads was transferred down to the rock, which wouldn't be too surprising with a 28-foot long pile. You can see some of the pictures, the tight working environment, working near the existing scaffolding, existing building. Project was completed without issue and no issues with vibrations or working in those overhead areas. Second project, this was different part of the country now. This was down in Tampa, Florida. This was going to be for a new pedestrian bridge that was going to cross over the major roadway there between a hospital office building as well as a new tower that was under construction. So challenges here included heavy column loads, as well as working between the two different areas in a constrained environment. And then also similar to, or typical for this area of the country, highly variable limestone. So when you look at the profile there, it was basically a up to 20-foot thick sand layer that was underlain by very soft clay. And then you get into that weathered limestone that was highly variable in terms of when it would develop into more competent rock. So in order to resist the loads that were shown there, the design team designed a, or the project team designed a solution that was going to be ductile iron piles, a different size here. This was a 118/75. So this is a smaller diameter pile with a 220 shoe, which would give you about an 8.5-inch diameter grouted pile that was good for, you can see there, about 75 kips compression with a center bar installed, about 30 kips of tension. And then there was additional lateral loads that were applied due to the loading on some of the foundations. So the project was performed by EarthTech, a Menard company, where they installed the exterior grouted piles. All the piles were driven down to competent rock where they achieved set. Because of the variability in the limestone, some piles were as short as 32 feet, others were deeper than, or up to about 70 feet. And because of the plug and drive nature, you're actually able to reuse sections as starter sections. And so they were able to deal with the variable rock conditions with very minimal waste. So the process would be installed as you're driving that pile. You're going to be pumping grout and developing that displacement pile. So from a design perspective now, a little different than the end bearing approach. Now you're going to be looking at developing frictional capacity along that grout to ground bond zone with the pile. It's very similar to a micropile in soil, essentially. So perform that work with very little vibrations, very few issues, and easy to mobilize between the two different sites across the street. A range of load tests were performed to confirm the design, so compression, tension, and lateral loads. And you can see each of these plots, the actual loads that were used for design were far less than what they tested. Over 300 kips applied for compression loads. You can see just over about a 1/2 inch of deflection. For tension, they put almost 90 kips in tension, and then for lateral, they went up to 18 kips. So very good performance of the system on this particular site. And there's a picture of the completed structure. So as we wrap up talking about ductile iron piles, a couple of notes here. It is a driven pile option. It's installed with a little bit different than traditional pile driving equipment, but it is driven in nature. So it helps address some of those challenges where maybe traditional piles are not going to work. It can be installed with a couple of different approaches, which give you versatility depending on the geotechnical conditions that you encounter on the site, as well as the loading conditions. It's got a moderate to high capacity, depending on what you're looking for. And that's particularly important for constrained access sites where you're trying to maximize the benefit of the piles on those tight sites. Because of the modular nature, along with the low vibration aspect of the work, works really well when dealing with interior applications, something that maybe you're considering a helical or a micropile application. If you're in less than about 25 feet, so say about 18 to 25 feet, it's common to have to cut the piles in half, and then you would use a drive-on coupler and be able to make that connection. If you've got more than about 25 or even 30 feet of overhead, so thinking specifically about a high bay warehouse, like you can see in the picture there, that is going to allow you to use full sections and perform this work very quickly without any issue related to the overhead. As we saw in that one example there, the plug and drive connections works very, very well to be able to adapt to highly variable subgrade conditions, particularly when you have variable rock depths, and do it with very minimal waste using the system. And then when we look at, specifically in the industry, I'd say about a third of the work that our installers get involved with are alternatives to micropiles. And that's going to deliver an alternative that's typically a much lower cost and faster alternative to micropiles. But then about a third of the work that we see is as an alternative to helical piles. And that's where the system oftentimes will give you a greater capacity. And in many cases will be used when there's concern about installation challenges associated with helicals, whether it's torquing up too early or spinning out on soft over hard ground. And so just another option for those specifically. So we have lots of information available, technical as well as case histories on our website. And if you have any questions, I'm happy to answer them as we get towards the end.
All right, Brendan, thank you very much. And our third presenter is Ian, and you have control. Ian.
Thank you very much. And hello, everybody. My name is Ian Vaz. I'm the assistant manager for the business development group for GIKEN America. And what I'm here to talk about today is a project where a unique method of pile driving of steel sheet piles was carried out for a project in the state of Delaware for a bridge replacement construction. So as the title reads, a vital utility that serves the northern part of the state needed to be protected from vibrations. Hence the specification and utilization of a non-vibratory pile driving method known as the press and piling method. So I will be sharing some details about this project and how this piling method, this press and piling method, was applied. All right, so the purpose of what I'm showing here on this screen is some information on this project. And the purpose of this construction was to replace an existing bridge that was constructed back in 1929. The project owner was the Delaware Department of Transportation. The engineer of record for DelDOT, or the Delaware Department of Transportation, was McCormick Taylor, who is based out of Philadelphia and actually was the engineer that specified the press and piling method for some of the construction here. The general contractor was Mumford and Miller Concrete, and they were the ones that were responsible for pressing in the sheet piles out of the town of Newport, which is in Newcastle County in Delaware. And just to give everybody an idea, Newport is northern Delaware. It's about 40 miles southwest of Philadelphia and about 130 miles southwest of New York City. And the construction was actually done right off of the Christina River. Now, the press and piling method was specified again for cutoff wall installation to protect this 72-inch sewer main that you see here. It was designed to protect the sewer main from vibrations that would occur during future bridge construction. And so this sewer main is a utility that runs throughout the county, pretty much the northern section or the northern region of Delaware. And it was imperative that the utility was protected from any damage that may have been caused from conventional pile driving because of how vital the utility is to that region. So, of course, the press and method was specified for that, and we'll get into a little bit about why it was specified. So, as you can see here with this video, these machines that are associated with the press and piling method that are commonly known as silent pilers, they're designed to grab onto the existing or the piles already installed, and it's designed to use the extraction resistance of those piles that are in the ground to press the next pile in. Now, that extraction resistance consists of the weight of the piles themselves, the skin friction around those piles, the interlock resistance in between the piles, and the weight of the machine itself. So those four factors allow the machine to use these forces to get the subsequent piles into the ground. Now, if you're wondering how the first pile is started, well, here is a steel component known as a reaction stand that opens up with outriggers and holds counterweight. Usually that counterweight is unused sheet piles since it is the beginning of the project. And so this setup allows the machine to keep grounded until it installs the first 3 pairs of piles into the ground, and it will slowly walk off of that reaction stand and onto the piles to move forward. Now, once the press-in force in tons is heavier than the machine itself, the machine can pick itself up and position itself closer to that pile to finish that pile, and then extend outward to be ready for the next sheet pile or sheet pile pair. And it will just continue that advancing operation for the remainder of the project. Now, as a non-vibratory method of pile driving installation, there is some vibration that is associated with it because it is powered by an engine unit or a power unit. But what I'm showing here is a chart that shows data from the German National Standards Organization, or DIN. And what they've done is give a comparison of numerous types of pile driving equipment. For press-in machines, they are represented in green here, with the piler itself, and then a piler with a continuous flight auger. This data is actually showing piles, machines that install U piles, but Z piles, which are predominantly used here in North America, have similar readings. But if we were to take a couple of examples in terms of distance, for example, here you have 8 feet or 2.5 meters. If we were to look at that, you can see that the peak particle velocity in inches per second would be 0.09. And from a distance of 5 meters or 16.4 feet, we're looking at about a 0.07 inches per second in peak particle velocity for that. And so the further you move away from the operation is the more imperceptible the vibration becomes. As for noise, this is another chart that shows data from a Singaporean agency known as the National Environment Agency. And in terms of noise levels, using the same equipment, you can see that from a distance of 5 meters or 16.4 feet, we're looking at about 73 decibels of noise. And from a distance of 10 meters or 33 feet, we're looking at about 70 decibels of noise. And we know that conversation levels are around 67 or 68 decibels. So this allows for conversations and communication to occur on site with this equipment. Okay, here is a video that is showing an example of how the pressing machine operates. Now, there are attachments that allow for the equipment to go through denser soil conditions. And this includes a water jetting attachment, usually used for silty or clay sands with blow counts between 25 and 50 blows per foot. And a continuous flight auger attachment that's designed to simultaneously drill and press in sheet piles. And that's typically used when the blow counts exceed 50. But for this project, it was very soft soils that were dealt with, so it was just the standard mode or standard method that was used on this project. Now, to get into the project itself, we're looking at a cofferdam and an abutment that was supposed to be constructed with pressed-in piles. Again, the reason for the pressed-in piles was to avoid any damage to the 72-inch force main that's shown here. However, one thing that occurred while the at the time of the project, when it was supposed to start, there was actually no pressing machines available at the time because of an ongoing project or upcoming project. And so what the contractor, Mumford & Miller Concrete, was allowed to do was vibrate these sheet piles on the outskirts of the cofferdam, as long as they didn't exceed any the vibration threshold, alert thresholds. And they're able to get many of those piles in on the outer parts of the cofferdam. But once they came around to this area is when they started to set off those alerts, and they had to stop piling. And you can see here that the distance between the edge of the force main and the pile alignment was 13 feet. So the contractor actually tried their luck on this end. They were able to install about 3 or 4 pairs before they started setting off the vibration monitoring alert thresholds there too. So they had to hold off until the machine arrived. And coincidentally, the machine did arrive a few days later. And so, speaking of that, with the piles that were already installed into the ground at both areas, that reaction stand that I just mentioned earlier of showing how the machine starts off was actually not needed. The machine was just able to be assembled onto the piles that were already installed. So here is an image of all of the equipment or the vibration monitoring, all of the monitoring instruments that were in place for that sewer main. That included inclinometers, piezometers, and seismic reading equipment as well. Here's just an example of the machine layout that would have been used for abutment A. This is where the reaction stand would have been placed, and where the machine would have walked off and installed the piles, the 80 linear feet of sheet piles. But again, there were already 3 or 4 pairs in place, so the reaction stand did not actually have to be used, which actually saved some time for the setup of that. Now here are the soil conditions where this boring area JS2 was where abutment A was placed. You can see how soft the soils were after the fill that was removed. And then the southern edge of Pier 1 was also where the pressing machine had worked to install the sheet piles, to press in the sheet piles. The green line is where is elevation minus 21.5. This is where Del Dot and McCormick Taylor required the sheet piles to go down to. But keep in mind, or with the pressing machine, in order for the machine to obtain a proper reaction to get the next piles in, 25-foot embedment is required into the ground. And so with Pier 1 being at a lower elevation than abutment A, these sheet piles had to go a couple feet below that minus 21.5 elevation in order for the machine to work properly. All right, and there was actually a concern with how soft the soils were on the project before it got started with the machine, where the concern was the machine actually pulling up on those reaction piles as it's trying to install those sheet piles. But that never actually happened here. We can see the soil conditions, and that 30-foot long PZC 13s were installed. And here are some images of the equipment being arriving onto the site and being offloaded. A very, very small area to offload here. There wasn't much room to work with, but you have the machine saddle here that's clamped onto the reaction stand. That's how it's typically transported. And that was the first to be offloaded here, along with the power unit. Of course, a second truck came with the remaining parts, or the remaining pieces of the equipment, including the leader mast and a chuck. And the chuck is responsible for the actual installation, grabbing onto the sheet piles as it's pressing them in. Now you can see where the crane is trying to work from here. This is a 110-ton crane, and you can see that with the sheet piles that were already vibrated in, The assembly of the machine was taking place on on those sheet piles. Each of these parts weighed 10 tons. And so the crane was pretty much at its limit for trying to get the machine assembled at that distance. And here's an image of the leader mast being placed inside the machine saddle. And here's an image of the chuck that was actually just connected into the leader mast. And this again is responsible for the sheet pile installation. And what we're looking at here is a view from behind showing the installation along Pier 1, the southern wall of Pier 1, where the crane is feeding the sheet piles to the machine as it's installing and continuing to move toward the east. All right, here's another image of the machine actually piling toward the east along this alignment here in this direction. Now, at no point during the operation did the machine or anything, any type of equipment exceed the alert level threshold, and then the alert levels or the threshold levels that were in place along that 72-inch force main. Really thanks in part to the pressing machine itself. And this chart is actually showing example of a few days where the press and piling machine was in operation. And you can see that it's pretty quiet throughout those few days, and at no point did it actually hit the alert level at 0.15 inches per second. And it also of course didn't hit the threshold level there. There were a few spikes that was apparent here and there, but they didn't go past 0.1 inches per second BPV. Now in this case, this is where the machine was actually moved from Pier 1 to abutment A to install the sheet piles, but they had to deal with some overhead power lines. And so there was splicing that was involved. And they actually, instead of using the 100-ton crane, they used a 15-ton smaller crane to pick up the sheet pile sections, put them into the machine, and splice them as they go in to complete the 30-foot-long sheet pile installation. And here's an example of the splice kit that was used for the operation. And here are some images of the splice kits being welded to the front and back of the machines. Of course, one splice was required, so the first section would go in, the machine would hold on to it. It would the welder would weld the splice kits on to that pile, and then the machine would finish pressing in that sheet pile and then move on to the next one. There was a slight hiccup when during the piling at abutment A, where the machine did actually run into some inactive utilities, but the back sheet pile of this pair was cut to be able to skip over those utilities and pile up, continue piling. Here's some images of the cofferdam. This was after the pressing machine had finished its work around that 72-inch force main. So there's a image of the cofferdam for Pier 1. And here's another image of a crane lifting a drill rig into that cofferdam to begin drilling for the construction of Pier 1. And there's an image of Pier 1 being constructed. And here's a later image of the bridge girders being laid down for the bridge piers as the new bridge is continuing to be built. This is a very recent image of the new bridge for James Street, with the old bridge not yet fully demolished. And here you have the rendering of the proposed new James Street Bridge. Right, all in part thanks because of the work that the press and piling method did without damaging that 72-inch force main. Here are some acknowledgements for helping get this presentation together. And I'd like to thank everybody for their attention.
Thanks, Sam. Thanks so much to all three of you. Hopefully everyone has a better understanding of these pile and pile installation alternatives that can be used under the relevant conditions. So I do have some questions for all three of you, and we should have enough time that if people want to keep throwing a few more questions out there, we'll probably get to them. Brendan, the first question is for you. Is there any concern with inducing liquefaction as you install those piles under that high
Sure.
speed?
Yeah, that's a good question, Travis. So what I would say to that is we've had a significant amount of experience in very loose or soft soils, whether it's loose sands, silts, or even clays. We haven't had issues with a liquefaction effect by the driven pile. And I think part of that is that it's not a super high frequency, like vibratory type energy. It is higher frequency than a traditional pile driver, but it's maybe 300 cycles per minute. And so the energy that you get isn't enough to really excite and build up pore pressure enough to cause liquefaction, at least in my experience. So we've had a lot of work that's been successfully installed in those types of conditions.
Mm-hmm. Corey, a question for you. So with the reduced modulus of these piles, do you have I mean, obviously you need to have a larger size, either impact or vibratory hammer to install a section. Do you have any sense? Like, do you need to double the size of a hammer? Or is that just too open-ended of a question?
That might be too open-ended of a question, but let me answer it this way. No, with the lower modulus of elasticity, that doesn't really impact or affect the driving of our product. So our product can be driven in all different types of soils, or we can look at different applications. So we've done rock socketing applications. We've done under-reaming bit applications. We've done, a whole variety. Generally, when we talk about installing our product, we ask that you hit it with around 15 to 20 KSI pressure. So if you're using a vibratory hammer, take the diameter of that product, 15 to 20 KSI, and that's our governing guidance at the moment with the approach.
Yeah. Excellent. Ian, do you have typical depths or maybe even maximum depths that you press in the sheet piling?
Yes. So the maximum would be the typical maximum is 78 feet. And that's because of I don't know if I think everybody saw the continuous flight auger that can be affixed to the machine for installation. Well, that limits the sheet pile length to 78 feet. There are extensions available to allow for a 98-foot long sheet pile installation. So that's possible too. So that's the max. Typical, there's not really a typical, it just all depends, but it does have to have, the sheet piles do have to have a 25-foot embedment in the ground. This allows mainly for the skin friction to be used to allow the machine to grab on and then use that extraction resistance to get the piles in. So I guess the short answer is anywhere from 27-foot long sheet piles to 98-foot long. And I say 27 because you do have the clamps on the saddle that have to grab the top 2 feet of the sheet pile.
One more question for you. How does the machine handle changes in directions? Like if you have to do a 90-degree?
Right. It's a little bit more complicated than with conventional piling methods. You do have to, let's say you're coming to that point where you're turning a corner. You do have to install a pair, the production pair, and then a dummy pair to form a T. And then you'll have the crane pick up the machine and put it on that T. So it'll be grabbing those 2 pairs, and they can use that to continue going in that direction.
Okay, excellent. All right, Brendan, someone has a question. What micropile or driven pile sections are commonly substituted with the ductile iron pipes? Do you have a range of them?
Yeah, so I guess if we look at it in terms of capacities, right? I mean, micropiles by all means they have a place in the industry. What we find is that if you're looking at a project that's specified for micropiles or considering micropiles, where there's concern about vibration and the capacities are generally less than 100 tons. That's really where there's some benefit. If you're trying to replace something that's a much higher capacity, if it's 150 tons or more on a micropile, we're not going to offer a one-to-one replacement, and that's where you lose a lot of the advantage of the system. And so, generally speaking, in that sweet spot is the 25 up to 100 ton range for us relative to micropiles.
Okay, excellent. Corey, another sort of open-ended question for you. What can you say about the sustainability or the environmental impacts of the FRP piles, maybe compared to the other pile materials?
Great question. So we've gone through several EPD, environmental product declaration studies. We can pass that on to the group. The state of New Jersey has found that our product is a non-leachating product, so we are environmentally inert. There's no microplastics, anything like that that's going to leach out. So in the state of New Jersey, we're one of the only products that is approved for some of their cranberry bogs and oyster hatchery areas.
Mm-hmm. Excellent. Brendan, one of the attendees is asking about the I guess that we basically say they're questioning the strength at the joints.
Sure. Yeah, absolutely. Great question. We get that quite frequently. Being that it's a modular system, that joint connection is really important. When you look at that material, if you just simply look at the cross section of that joint, it's actually substantially thicker than the pile material itself. And we know through testing that the plug and drive connection will form a continuous section as you drive it. And so what results then is that it doesn't affect the axial capacity. And when you start looking at lateral capacity, we've done a lot of tests on this. What you'll find is that the properties of the main pile section is actually going to dictate the lateral behavior. So as long as you're designing for that main section versus the oversized plug and drive connection, you should be good to go relative to axial and lateral.
Mm-hmm. Excellent. And then for the dry installations, it seems like you were talking specifically to end bearing conditions. Do you install them in the dry for friction capacity?
Occasionally. So we have had a few projects where looking for the ability to get friction, not going down to something that's a really competent material. It's been a medium dense sand versus a very dense. The challenge with that is that you're not going to develop a real high capacity out of it because these are small diameter. So It is possible. It is an application, but there's not a lot of bang for your buck out of the system.
Yeah. Excellent.
So, yep.
Well, thanks to all three of you. And those are really, really good answers to all those questions. So thanks again to all three of you, and thanks to our attendees. And here is your details on your PDH certificates. If you, I believe that's if you paid the registration fee in order to get the PDHs through DFI, if I have that right. And our next webinar is scheduled for the 6th. I had the 4th of September written down, so I guess I've forgotten that we skipped that one for DFI annual. So November 6th will be the next Impact webinar. So thanks again to the presenters, and thanks to everyone for your time. Have a good day.
Our pleasure. Thank you.
Thank you, everybody.